Let's move on to another. Example 24.2. 3-point charges are oriented at corners of a square that measure 82 centimeters per side, as shown in the diagram. Charges A and B are negative charges, and C is a positive charge. All three charges have a magnitude of 8.0 times 10 to the negative 15th coulombs. Find the net force on charge B due to the forces from charges A and C. We are looking for the net force on charge B, which is negative, due to charges A and C. In this diagram, let's indicate what the directions of those forces are. The force on B due to A is repulsive, so B is going to be pushed to the right by charge A. The force on B due to C is attractive because I have unlike charges. So FBC is going to be an attractive force. It's at a 45-degree angle. Now, we're trying to find the net force. So you could think of this as a vector problem if you wanted to. What is vector FBA plus FBC? We could actually sketch that, but we need to know something about the magnitudes of the vectors. And in order to figure out what the magnitudes are, we have to apply Coulomb's law. These forces are not equal to each other because the distance between the charges A and B are not the same as the distance between charges B and C. I can't just say, well, I can draw what this force is going to look like. I need to know what the scale is and what the magnitudes of the forces are. And I have to use Coulomb's law to help me do that. So here's my writing of Coulomb's law. Fij is equal to K times Qi times Qj divided by Rij squared. And now we've got I and J going to be representing A and B in one case and B and C in another case. I'm told that the distance between A and B is 82 centimeters, but I'm not told what the distance between B and C is. But I can use the fact that this is a 45-45 90-degree triangle. I can use a variety of means of figuring out what this distance h is. H, I think, means hypotenuse in this triangle, so you could use the Pythagorean theorem, or you could use a trig function if you wanted to. Doesn't matter which one, but somehow you need to figure out what's the distance between B and C. I'm going to use the Pythagorean theorem. So the hypotenuse is going to be the square root of the sum of the squares of the two sides, and my calculator tells me that that's 115.97 centimeters. That's what I'm going to call RBC, the distance between charge B and charge C. So now let's figure out what the magnitudes of these forces are. I'll apply Coulomb's law. Let's work on charge B and A first. So there's Coulomb's law in symbols, and now I need to put in the numbers. And now I'll feed those numbers into my calculator, and I find that the force on B due to A is equal in magnitude to 8.57 times 10 to the minus 19. That is the magnitude. The direction is to the right. Now let's figure out what the force on B due to C is. So there's Coulomb's law, and now I'll put in the numbers. And now I'll feed those numbers into my calculator. Notice that this force is going to be smaller than FBA because the distance between B and C is bigger than the distance between B and A. So I find that the force on B due to C is equal to 4.28 times 10 to the minus 19 newtons. The direction of that force is down and to the left at a 45-degree angle. We want to know what the net force is. The net force is going to be equal to the sum of those two forces, which are vectors. And now we can bring out our vector methods. We've got two forces, we know their magnitudes, we know their directions. What we want to do is we want to break those forces into components that are along the x-axis and along the y-axis. Add the x components together, add the y components together. We're going to get some resultant vector, and then we're going to find the magnitude and the direction of that resultant vector. So if you like, you could do a tail-to-tip method of sketching these vectors. That's what I'm going to do. I'm going to use a scale. 1 centimeter is equal to 1 times 10 to the minus 15 newtons. And I'll sketch these vectors to scale. So here's the origin of my coordinate system. FBA is going to be along the plus x-axis, and it's going to have a length 8.57 centimeters. Now the tip at vector B, I'm going to draw another origin and sketch vector FBC. So I've got to measure down 45 degrees, and now I have to sketch a vector that is 4.28 centimeters long. So the resultant vector is going to go from the tail of the original vector to the tip of the last vector. And I'm going to say that it makes an angle of theta with respect to the positive x-axis. Now, I've done a graphical addition of this vector. I now want to do an analytical addition of this vector. Graphically, I find the length of this vector with a ruler. It's about 6.3 centimeters long. So graphically, that's going to be about 6.3 times 10 to the minus 15 newtons. And using a protractor, I measure that angle theta to be about 25 degrees down from the plus x-axis. But I'm not satisfied with that graphical addition. I want to know what it is analytically. And so I'm going to employ these analytical vector methods. First, FBA I recognize has no y component, so it's only x. It has no y part. On the other hand, FBC has x and y components. FBC is going to have an x component that's in the negative x direction and a y component in the negative y direction. So I'm going to sketch a force triangle for FBC and a force triangle for the net force that's on B. So there are my force triangles, and I'm going to resolve FBC into x and y components. I'm going to work on the y component first. FBCY is FBC times the sine of 45 degrees. And now I'll put in the numbers. And I get some result in my calculator. So the y component of the FBC triangle is 3.03 times 10 to the minus 19 newtons. I now play the same game with the x component. And that's related to the cosine. Now I put in the numbers, and I get some result. The x component is also 3.03 times 10 to the minus 19 newtons. The reason for that is that this was a 45, 45, 90 triangle. Now I'm ready to find the net force on the object. I'm going to see that according to this diagram, it has an x component, which is equal to FBA minus FBC in the x direction. And now I need to scroll back up and see what FBA is. FBA is 8.57 times 10 to the minus 19 newtons. Let me put in the numbers now. And I'll feed that into my calculator and get some result. I find that the x component of the net force on B is 5.54 times 10 to the minus 19 newtons, and that is to the right. Now let's work on the y component. The y component is going to be the same as FBC in the y direction, because there is no y component of FBA. So it has a y component of 3.03 times 10 to the minus 19 newtons in the downward direction. So now I know the horizontal leg of the net force triangle. That's 5.54 times 10 to the minus 19 newtons. And I know the vertical leg of this net force triangle, 3.03 times 10 to the minus 19th newtons. I want to find the hypotenuse of that net force triangle, so I'm going to use the Pythagorean theorem. And so I'm going to put in the numbers, and I'll feed it into my calculator. And I get 6.31 times 10 to the minus 19 newtons. Notice that that's not bad compared to what I got graphically up here. Now let's see if I can get the angle. I'm going to use the tangent. And in my force triangle, that the angle theta, the tangent of that angle is going to be the opposite side, the y component, divided by the adjacent side, the x component. So let me put that together. And now let me feed in the numbers. And now I'll put it into my calculator. And I get that the angle is 28.7 degrees. A little bit larger than my graphical result, but still not bad. So finally, let's put it all together and say that the net force on B is equal to 6.31 times 10 to the minus 19 newtons at 28.7 degrees down from the plus x-axis. And there is my final result. Lord have mercy, Mr. Haynes. Have I got to do all that in order to solve this problem? Yes, you do. Let's review what we did here. We saw that we had a diagram in which we had 3-point charges. Forces were exerted. We figured out what the direction of the forces were. We used Coulomb's law to figure out the magnitude of the forces are. Then we sketched a diagram and did a vector sum to figure out what the net force was. And finally we got what that net force was.